Hi. What's up, Shada? What's up, Leo? Gold hate. Hope everybody had a good weekend and are subsequently having a great start to the week here on good old Monday. So we got third week of online learning. That's pretty crazy. Spring break was 3 weeks ago. Seems like forever. When will we have a practice performance task? I'm not sure what that question means. Like, when will we have a performance task? I don't get what a practice. You mean like just like review for the performance task? Review. Okay. Yeah. So here's the plan. Today and tomorrow. So this lesson will probably go through today and tomorrow. If I rushed a lot, I could probably get it through all today, but I don't want to do that. I don't want to take the a full hour out of your lives here. So we'll probably do this lesson today and tomorrow. And then Wednesday will be like, I won't have like an actual lesson for you. I'll send you a review on Wednesday morning. I'll be here during this time to answer any questions you have or in office hours. And then Thursday, I'll actually send you the performance task. But so yeah, Wednesday is when you should expect the review. So for solving this stuff, we just send you our answers. Yeah. So just like we did with the the vacation, the murder mystery checkpoint. Yeah, just send me the answers in whatever the best way for you is. And we won't be on Zoom or anything. I'll just, I send you it, you work on it, you send it back to me. Right, probably just like sometime by the end of the day, Friday. So I'll send it to you Thursday, and you have all of Thursday and, afternoon, evening to work on it, and then all day Friday as well, and just, send it to me by the end of the day, Friday sometime. All right, so back to our logarithms, we ended on talking about solving equations, logarithmic equations. So let's jump back into that. And when I look at this one, so I notice that I have one single logarithm here. Okay, so what I'm going to do is I'm going to isolate this logarithm and then use exponential. So first step, I will subtract 3 from both sides. 3 minus 3 is 0. I will divide -6 on both sides. So log base 5 of 4x minus 11 equals 0 divided by -6 is 0. Okay, so now we learned that if I want to get rid of logarithm, I need to use exponential to get rid of it. So I will make an exponential of base 5. And all that stuff that I originally just had gets moved up into the exponent. And reminder, we choose 5 as our base because that's what the base of the logarithm was. And when I have that, the whole reason I choose that is because they will then cancel. So I'm just left with 4x minus 11 equals 5 to the 0 power. Anything to the 0 power is just 1. So 4x minus 11 equals 1. Add 11 on both sides. 4x equals 12. And I get x equals 3. For number 2, natural log of 2 plus natural log of x minus 3. So the thing that I first notice about this is that it's natural log, and they're being added together. So from our properties, we know that we can combine those together so that this is natural log. Wait a minute, why did I write it like that? I never write it like that. I've changed. Natural log of 2 times x minus 3. Right, we see the addition between the logarithms on the outside. That means we can combine them on the inside by multiplication. 2 times x minus 3 equals 4. And so I will distribute here. Natural log of 2x minus 6 equals 4. So now somehow I need to get rid of natural log. Now natural log hopefully we remember is base e. So I will make an exponential of base e. And everything that was originally the equation gets moved up into an exponent. E and natural log will cancel each other. So that I have 2x minus 6 equals e to the 4th. E to the 4th, it doesn't look great, but it's just a number, right? E is just a number, so some number to the 4th power. But I want to actually calculate what that is because I don't want whatever the decimal is. So I'll just solve it like this. Add 6 to both sides. E to the 4th plus 6. Divide 2 on both sides. So x equals e to the 4th plus 6 divided by 2. I was late because I was playing Fire Emblem. Classic, man. Gets me every time. I was late to my staff meeting last week because I was playing Fire Emblem too, man. It's tough. I get it. I empathize. But I'm just glad you're here now. All right, so we're going to talk about a couple different applications of logarithms. Now, one of the biggest, most relevant things in terms of exponential or growth or logarithmic growth, a logarithmic growth model, is what's happening in the world right now, right, with the coronavirus, which you've probably heard or seen a lot of graphs of exponential growth. Probably less talked about, but still important, especially when you consider different scientific data, is considering the logarithmic growth of the data. Okay. But so a couple of the things that we're going to specifically talk about is one, which is the Richter scale. You've probably at least heard the Richter scale before, at least the name. And that's what we use to measure earthquakes, right? How powerful an earthquake is. So this is that first equation, or this is the equation that we use to calculate capital M to represent the magnitude of the earthquake, equals common log. So even though we can't see it, that's a log base 10. So common log of I divided by I0. Now, what exactly is I and I0? I is what we call the intensity of the earthquake. I0 is what we call the intensity of the threshold quake. Now, what in the world is a threshold quake? Threshold quake is the smallest detectable earthquake by us. Right, so maybe you've seen a Richter scale. It's kind of like it does the readouts. It like has the needle that like goes back and forth, right? And when it starts going really big, that means it's a really bad earthquake. All right, kind of looks similar to like a polygraph test too, like a lie detector. It starts to go out of control whenever someone's lying, theoretically. Okay, so I0, the intensity of the threshold quake, it's the smallest amount that we can actually measure, right? There are things that shake that are smaller than that, but it doesn't matter to us because we can't actually detect it. So if we can't detect it, then who cares is basically the thought process and how we make this formula. So what it does inside of here is that this compares the intensity of the earthquake that I'm talking about compared to the intensity of that smallest possible earthquake, right? And it takes the ratio of them. It divides them. Another way we can think about that is I can compare two specific earthquakes. So we'll look at problems where we want to know the ratio of two specific earthquakes. Right, we're saying this earthquake happened here in wherever, and this earthquake happened over here in wherever, and we compare those two. Well, then if we do that, then the answer, the thing that we get over here is not just what's the magnitude. It is the difference in magnitude. Between those two earthquakes. All right, so if we want to think about it in the kind of standard way, where it's just comparing to the threshold quake, then M just tells you, yeah, what's the magnitude of the earthquake? What is it? But if we compare two specific earthquakes and look at the ratio of those intensities, then the answer that we get tells us the difference between the two. Decibels is the other kind of main. It's a very similar formula, which is why I've chosen earthquakes and sound to do this. All right, decibels measure sound, how loud something is, and the formula is almost identical, save for this coefficient of 10 in front. All right, that's the only difference in the two equations. So just remember that sound has that extra coefficient of 10. I is the intensity of whatever sound we're looking at. I0 is the intensity of the threshold sound. So similar, threshold sound means the smallest detectable sound, right? There are sounds that are smaller than that are quieter than that, but does it really matter? Because we can't even detect them, right? And just like earthquakes of that needle going back and forth is because earthquakes are based on waves, right? Not like ocean water waves, right? And then decibels are sound waves. Okay, so that's why we kind of talk about these similarly. They're both kind of thinking about waves. And so there are some waves that are smaller than the threshold sound or the threshold quake, but we can't detect them, so whatever. All right, same deal here. Or we can compare two sounds specifically, right? Sound 1 compared to sound 2. Then this M gives us the difference between the two sounds. Quick little interesting reference. Interesting depending on who you are. I think it's interesting. So this is the chart for how we measure earthquakes in terms of what the actual numbers are. So we usually... You'll often hear earthquakes talked about like that earthquake was a 4.5 or a 3.2 or a 9.1 or whatever. Okay, but it's typically just in terms of tenths, right? Just one decimal place. And so these are the different ratings. It goes anywhere from a micro earthquake all the way up to a great, major, strong earthquake. And then on the right here is about how frequent they are, right? So like a moderate earthquake, there's anywhere from 1,000 to 1,500 per year. It can cause damage, especially to things that aren't built for earthquakes. Everyone will feel it, but pretty much not a lot of damage to general buildings that are built to withstand it. Right. All the way up to like, major earthquake, it's about 10 to 20 per year. Okay, causes damage to buildings, things can collapse. And then lastly is like a great earthquake. Right, anything that's a 9.0 and greater, that's usually only happens, very rarely. One, maybe 10 to 50 years. Okay, but that's talking about complete, total destruction, right? Collapse of any buildings, heavy damage, shaking, and permanent changes to the ground, right? It changes the terrain permanently. Right, so just kind of an interesting reference. Okay, but the last thing the world needs right now is earthquakes, but they are still happening, luckily. It's just our luck. Okay, so quick example. An earthquake is 170 times more intense than the earthquake threshold. What is its rating on the Richter scale? Okay, so my capital I, the intensity, the problem tells me is 179,000 times the threshold. So 179,000 times I0. Now, if I go back to my formula for earthquake and Richter scale, etc. Right, I remember, so that yellow highlighted portion. So what goes inside of that logarithm is I divided by I0. Okay, so when I go back to my current problem, I'm actually going to move that I0. I'm going to divide both sides so that it's I divided by I0 just equals 179,000. Right, because again, when we say one is more intense than the other, what that's telling us is the ratio between them is 179,000. Now let's put it into our formula. M equals log of 179,000. Let me pull up my wonderful TI-84 graphing calculator. This stream sponsored by TI-84. So all I got to do is common log 179,000. Boom. All right, and again, for earthquakes, right, doing these log applications, we're just going to round to the 10th, first decimal. Right, you will. I don't think you'll ever hear an earthquake described as like a 5.253. No, they'll just say 5.3. This is on a PFA, right? Yes. This is on the log properties and equations, I think is what it's called. Whatever the PFA is that has the word log in it. Certainly. How did you bring the log? Just from the formula. Oh, on the calculator? It's a... Sorry, I lost it here. Just that button. It's right next to the 7. Or if you have a TI-84, it's just right to the left of the 7. It just says log. Does that answer your question? Yeah. Okay, cool. Yeah, it's just a common logarithm. Okay. Let's go to our next one. A conversation is 89,000 times more intense than the sound threshold. How many decibels is the conversation? So the big important part here, 89,000 times more intense. Okay, so the intensity of the conversation, just like last time, so I'm starting off just intensity. It tells me 89,000 times the sound threshold. All right, so 89,000 times I0. But if I look at my formula for decibels and finding out how loud something is, inside the logarithm is I divided by I0. So again, I'm going to divide both sides by I0 just to give me 89,000. And now we use our formula, which this formula does have the 10 in front. Okay, so all we got to do is just 10 log 89,000. So 49.5 decibels. So those two versions of using these are the very straightforward. We're told immediately this is this many times more intense than the threshold. So find the decibels or find the rating. Right, and it's just immediately plugging in and solving for calculating the answer. Okay, not a lot of intense thinking that we need to do in terms of solving or manipulating things. It's just plug in, go, get an answer, score a touchdown, win the game. So let's move on a bit from that. Let's add in a smaller step. Okay, not crazy. Okay, let's work backwards from here. And let me get rid of this calculator. So let's say I start off by knowing I know the two ratings of an earthquake, and my question is, how many more times intense is an earthquake that registers 7.1 compared to an earthquake that registers 6.3? Okay, so now I know the ratings. I'm working backwards to figure out what is the difference, or not the difference, what is the ratio of the two intensities? Right? How many more times intense is that 7.1 compared to the 6.3? So I'm going to go back to that secondary way we could think about these equations, which is by drawing a random blue line on the left side of the screen. Let's try again. Aha. Okay, which is this, where if I know the difference in the magnitude between the two earthquakes, I can set that equal to the logarithm, and then on the inside of the logarithm would be the ratio of the two intensities. Right? And currently, this is what my question is asking for. It's saying, solve for this. How much more times intense is the larger earthquake compared to the smaller earthquake? Right, so we have everything we need. We just have to solve it a little differently. We kind of got to work backwards. So let's first just figure out what is the difference in the two magnitudes. Okay, don't ask me how I got this, but it's 0.8. Right, so just subtracting the two magnitudes. What is the difference between them? 0.8. Now, that's not my answer. If you're taking this on a PFA, I guarantee 0.8 will be one of the choices that you can choose. Okay, but the question is not asking what is the difference in magnitudes. The question is asking how many times more intense. So 0.8 is important for us to use, but we don't need it right now. We do need it right now. It's just not our final answer. Right? We have to use that to figure out the next piece. Okay, so I'm going to use that 0.8 equals log of, okay, so we'll say, just to label these, we'll say earthquake 1 was the 7.1 and earthquake 2 is the 6.3. Always make sure to make your larger earthquake the first one, or the one that's, at least the one that's on top. Okay. Right, put the more intense or the highest rating of the largest sound, whatever. Make sure that's the top one. Okay, so I want to solve this equation. So this is just a logarithmic equation. This is basically what we did on the warm-up. I have a logarithm on one side equals some number on the other side. So in order to get rid of the logarithm, common log I know is base 10. So I'm going to create an exponential of base 10. And the stuff gets moved up into exponents. The 0.8 is now an exponent. Log of intensity of first divided by intensity of the second. Common log and exponential base 10 cancel each other. So on the right, all that's left is intensity 1 divided by intensity 2, the ratio of the two intensities. For the left side, I'll bring up my calculator. 10 to the power of 0.8, 6.3. So what does this actually mean? So the intensity, or actually, here, let me write it like this. Earthquake 1 is 6.3 times more intense than earthquake 2. Right, that's what that 6.3 represents. Because, again, this is equal to the ratio between those two intensities. So intensity 1 is 6.3 times more than intensity 2, or earthquake 1 more than than earthquake 2. A bit different in how we work backwards. All right, let's do a similar style question, but with the sound decibels. Hold up. Okay. A motorcycle, 95 decibels. Why am I highlighting? Motorcycle is 95 decibels. Lawnmower is 65 decibels. And the question I want to know, how many more times intense is the motorcycle than the lawnmower? Okay, so exact similar style. I know the actual decibel values, 95 and 65. What I want to figure out is what does that mean in terms of the intensities? Okay, so first things first, I first want to know what is the difference in decibels. So 95 minus 65. It could be anything. I'm going to take a wild guess and just put two random numbers down. Maybe these are true. Okay, the difference in decibels, 95 minus 65 is 30. Again, if it helps, let's list out some information. So, motorcycle, 95 decibels. Lawnmower, 65. So let's use this 30, the difference. We'll set that equal to, we'll set our equation equal to 30. Now remember, the decibel equation has the 10 in front. So 10 log times the ratio of the two intensities. Now remember, which one should go on top? The larger one, right? Or the larger one, the stronger one, however you want to think about it. But in this case, the intensity of the motorcycle should go on top because it is the louder sound. It's 95 decibels. Compared to the intensity of the lawnmower, right? It's the smaller one, the weaker one, so it goes on bottom. And now we just need to solve this equation. All right, so let's isolate the logarithm first. So we'll divide 10. 30 divided by 10 is 3. Common logarithm is base 10. So we'll just take both sides to the 10, or with an exponential. So 10 to the third power and 10 to the logarithm of the ratio of the intensities. But on the right side, the exponential base 10 and the logarithm base 10 will cancel, so I'm just left with what's inside the logarithm. Right, so the ratio of the two intensities is 10 cubed, which is 1,000. Okay, but what's important for these is, do we actually understand what the hell these numbers actually mean? Right? I have a random cool number here. What does this actually mean? Well, it means, again, look at what our label is. The intensity of the motorcycle divided by the intensity of the lawnmower is 1,000. So, in terms of our problem, the sound of the motorcycle is 1,000 times 1,000 times greater. Yeah, basically. But we're going to be a little more specific and say 1,000 times more intense, since it represents the intensity, than the sound of the lawnmower. All right, so even though the difference is only, it's only 30 decibels, which doesn't seem like a ton, right? Oh, this one's 30 decibels larger than the other. Well, in terms of the intensity of the sound, so if I'm thinking about the waves that make the sounds, right, that the motorcycles, those sound waves are 1,000 times as large as the lawnmowers. What in the world did I spell down there? I literally spelled lawnmower. Okay. All right, so we're going to pause there. Again, we have 2 more problems, but they're a little more involved and a little bit different. So we're going to save those. We're going to do those tomorrow. That way I'm not rushing through them. So we'll finish that up tomorrow. We'll talk about our We'll talk a little more. I'll reiterate about the performance task. Maybe I'll just go ahead and send you the review tomorrow. That might be better. So I'll have an assignment for you tomorrow at least with some practice problems after we finish talking about all these. It's not super long or anything. So I'll send you that tomorrow as well. We'll talk and finish up our notes. Wednesday review, Thursday performance tasks, due by the end of the day Friday. That's the setup for right now at least. That's what I'm thinking.